Welcome to the channel. If you're new here, I generally talk about persistence, how structures survive long enough to matter or become matter. I look at the universe through a simple lens. What lasts, what closes under constraint, what survives long enough to shape reality. Today's video is different. Today we're not asking what we believe. We're not asking what sounds interesting. We're not asking what feels mathematically elegant. We're asking something much sharper. What would actually move the needle? At the center of our galaxy sits Sagittarius A, the supermassive object around which stars orbit at extraordinary speeds. For decades, the dominant interpretation has been that it is a Kerr black hole, a rotating solution of general relativity. But there are alternatives. Some propose a fermionic dark matter core, a dense, degenerate object formed from keV scale particles. Others propose a mini Boson star, a horizonless scalar field configuration that can mimic a compact object from the outside. All of these models can, in some regime, look similar from a distance. They can fit certain orbital data. They can produce ring-like images. They can be made to resemble a black hole under specific conditions. So the question is not whether they can look similar. The question is whether they close the same constraints under the same observables. That is what this video is about. We are going to take three models, Kerr, a fermionic core, and a mini boson star, and evaluate them using the exact same measurable quantities, not philosophy, not preference, not theoretical beauty, measurable constraints, the S2 orbit and its precession, the limits on extended mass inside that orbit, the 230 gigahertz thick ring diameter measured by the Event Horizon Telescope, and the surface reprocessing bounds that rule out certain horizonless objects. We are going to ask very calmly which models close these constraints cleanly, which ones survive in narrow corridors, and which ones require additional assumptions. This is not about winning. It's about persistence under constraint. And here's the important part. We are not in a position of ignorance. We are not waiting blindly for random discoveries. We already know what would move the needle. We know exactly which future measurements would change the ranking of these models and which ones would not. That puts us in a strong position. So in this episode, we'll lay out each model carefully. We'll describe how it works. We'll examine how it responds to each constraint. We'll build a ledger, and then we'll step back and synthesize what actually survives. Because at the center of the galaxy, as everywhere else in physics, what persists is what closes. Let's begin. Section 1, the observable reality. Before we compare models, we have to anchor ourselves in what is actually measured, not interpretations, not theoretical preferences, measured quantities. At the center of our galaxy sits Sagittarius A, a compact radio source located about 26,000 light-years away. Over the past several decades, independent teams have tracked stars orbiting this object with extraordinary precision. From those stellar orbits, we infer a central mass of roughly 4 million times the mass of the Sun, concentrated into a region smaller than our solar system. That mass estimate does not depend on whether the object is a black hole or something else. It comes directly from orbital mechanics. The most famous of these stars is S2. S2 completes an orbit in about 16 years. At its closest approach, it passes within roughly 120 astronomical units of the central object. That is about 3 times the distance between the Sun and Pluto. At that distance, S2 moves at several percent of the speed of light. Its orbit is not a perfect ellipse. The periapsis advances slightly with each revolution. That advance, the Schwarzschild precession, has been measured and is consistent within current uncertainties with the prediction of general relativity for a compact central mass of about 4 million solar masses. This gives us our first constraint. Any viable model must reproduce not only the overall orbital shape of S2, but also the measured magnitude and sign of its periapsis precession. It must do so without introducing detectable additional mass gradients across the radial range sampled by that orbit. In other words, the gravitational potential across roughly 100 to a few hundred astronomical units must be extremely close to Keplerian, with only the small relativistic correction that is observed. There is a second constraint embedded in those same data. When researchers fit S2 and other stellar orbits, they also test for the presence of extended mass distributed within the orbit. If there were a significant amount of non-central mass, a dense cluster of objects, dark matter, or some diffuse core structure, it would alter the orbital dynamics in a measurable way. Current analyses place tight upper limits on any additional mass inside the S2 orbital scale. The fraction of mass that can be distributed rather than centrally concentrated is small. Whatever sits at the center must behave across those radii almost exactly like a point mass. Now move from stellar dynamics to imaging. In 2022, the Event Horizon Telescope released its first image of Sagittarius A at 230 gigahertz. The result was a ring-like structure with a measured thick ring diameter of approximately 52 microarcseconds. That angular scale, when combined with the independently measured mass and distance, the mass to distance prior, corresponds to the gravitational scale of a 4 million solar mass compact object. The thickness, brightness, asymmetry, and size of that ring form our third major constraint. Any model must reproduce a ring-like emission structure at roughly that angular diameter under the same mass and distance scaling. This is important. The observable reported by the EHT is not simply a theoretical shadow diameter. It is a thick emission ring reconstructed from interferometric data and calibrated against a library of simulations. When we talk about matching the EHT result, we are talking about matching that observable, not a generic photon sphere radius, not a central depression measured under a different definition, but the thick ring diameter as extracted in the analysis. There is a fourth constraint that receives less public attention but is equally important. The EHT analyses also test for the presence of a radiative surface. If the central object had a hard surface rather than an event horizon, accreting material would release energy differently. A fully thermal, luminous surface at the required scale is disfavored by the observed spectrum and size constraints. A perfectly reflective surface is also unlikely under current analyses. That does not automatically rule out all horizonless objects, but it places boundaries on how they can behave thermodynamically. So at this point, before we discuss any specific model, we have four observational pillars. First, the S2 orbital shape and its measured relativistic precession. Second, the tight limits on extended mass within that orbital region. Third, the 230 gigahertz thick ring diameter measured by the Event Horizon Telescope under the known mass-to-distance scaling. And fourth, the constraints on surface reprocessing behavior derived from imaging and spectral consistency. These are not speculative constraints. They are not philosophical. They are quantitative, repeatable, and independently cross-checked. Whatever lives at the center of the Milky Way must close all of them simultaneously. That is the ground we stand on before any model enters the conversation. Section 2, Kerr black hole. The first model we examine is the Kerr black hole, the rotating solution to Einstein's field equations in vacuum. It is defined by remarkably few parameters. In its simplest astrophysical form, it is characterized by a mass and a spin. Everything else, the geometry, the horizon, the photon region, the frame dragging effects, follows from those two quantities. One of the reasons Kerr has become the default interpretation for Sagittarius A is not tradition, it is constraint economy. With only a central mass and a spin parameter, it naturally produces a gravitational potential that behaves like a point mass at distances large compared to the gravitational radius. That immediately explains why stellar orbits, including S2, follow nearly perfect Keplerian ellipses with only small relativistic corrections. When we look at S2 specifically, the measured prograde periapsis precession is consistent with the Schwarzschild component of the Kerr metric for a 4 million solar mass compact object. The magnitude of that precession matches the general relativistic prediction within current observational uncertainties. There is no need to introduce additional distributed mass or exotic corrections to explain the data. The geometry of spacetime itself accounts for the deviation from a closed ellipse. The second constraint, limits on extended mass inside the S2 orbital region, is also naturally satisfied. In the Kerr picture, essentially all of the mass is centrally concentrated. Any additional distributed matter, such as stars or dark matter, is treated as a small perturbation. Current observational limits allow only a small fraction of extended mass within that region, and Kerr does not require any more than that. The gravitational field across the S2 radial range remains extremely close to that of a point mass. Now consider the Event Horizon Telescope result. In the Kerr framework, light rays near the black hole are strongly lensed. There exists a photon region that defines a characteristic angular scale. When plasma accretes and emits at millimeter wavelengths, general relativistic magnetohydrodynamic simulations show that the observed image forms a thick emission ring surrounding a central brightness depression. Under the independently measured mass and distance to Sagittarius A, the predicted angular diameter of that ring aligns with the observed value of roughly 52 microarcseconds. The key point here is not that Kerr produces a ring. Many compact objects can produce ring-like features under certain emission models. The key point is that Kerr produces the correct ring scale with minimal assumptions once the mass and distance are fixed by stellar dynamics. There is no need to tune additional structural parameters of the central object to land at that angular diameter. The gravitational scale set by the mass-to-distance ratio naturally places the ring in the observed range. Finally, there is the surface constraint. A Kerr black hole possesses an event horizon, not a material surface. Matter that crosses the horizon does not re-radiate from a hard boundary. That automatically avoids the class of constraints that disfavor luminous thermal surfaces at the observed scale. The absence of a surface is not an added feature, it is inherent to the solution. Taken together, Kerr closes the current constraint set cleanly. It reproduces the S2 orbital behavior and precession. It respects the tight limits on extended mass within the S2 region. It aligns with the EHT thick ring diameter under the known mass and distance scaling. And it does so without introducing additional microphysical degrees of freedom tied to the central object itself. This does not mean it is immune to future falsification. A closer-in star could reveal multipole deviations. More precise imaging could detect departures from the Kerr geometry. But under the present observational landscape, Kerr survives without requiring structural adjustments. In the language of persistence, Kerr is the model that currently closes under constraint with the fewest moving parts. Section 3. Fermionic core, RAR. The second model we consider is a fermionic dark matter core, often referred to in the literature as an RAR type solution. In this picture, the central object is not a black hole, but a self-gravitating configuration of fermions, particles obeying the Pauli exclusion principle, supported against collapse by degeneracy pressure. The same quantum principle that stabilizes white dwarfs and neutron stars is invoked here at a different mass scale. In these models, the structure is not just a core, it is a coupled core halo system. The inner region forms a very dense, compact configuration where degeneracy pressure balances gravity. Surrounding it is a more diffuse halo that connects to the larger scale dark matter distribution of the galaxy. The appeal of this framework is that it attempts to unify the central compact object and the galactic dark matter profile into a single thermodynamic solution. Now, at large distances, a sufficiently compact fermionic core can mimic a point mass. If the core radius is small compared to the orbital radii being measured, the gravitational potential sampled by stars like S2 becomes nearly indistinguishable from that of a black hole. This is where the so-called compact corridor appears. For particle masses in the few hundred keV range, the inner core can become small enough that the mass gradient across the S2 radial shell is effectively negligible. This is important. The key dynamical quantity is not simply the total mass enclosed within S2's orbit, but the change in enclosed mass between periapse and apoapse. If that change, the effective mass difference across the orbital shell, is extremely small, then the potential remains almost perfectly Keplerian over that region. In that case, the orbit will look like it is responding to a point mass, and the relativistic precession can be matched within observational precision. In the RAR framework, certain high compactness configurations are constructed specifically to satisfy this condition. The reported effective mass difference across the S2 radial range can be orders of magnitude below current observational limits. In that narrow corridor, the fermionic core behaves dynamically like a black hole at the S2 scale. But this is where the constraints begin to branch. First, the extended mass constraint becomes radial shell dependent. A star with a periapse of 500 astronomical units, even if it provides tighter formal limits in that shell, does not probe the inner 100 AU region that S2 reaches. The fermionic model may be stealth at one radius and divergent at another. So each newly discovered star constrains a different radial layer of the gravitational field. The model survives only if it remains compact enough across all observed shells. Second, we move to the imaging constraint. The Event Horizon Telescope measures a thick emission ring at 230 gigahertz. In the Kerr case, that scale follows directly from the gravitational radius. In fermionic core models, the situation is more delicate. Depending on the compactness of the core and the emission prescription used, the size of the central brightness depression and surrounding ring-like structure can vary substantially. Some published configurations produce central scales significantly larger than the observed ring diameter. Others produce scales that are smaller. Matching the exact thick ring observable requires not just compactness, but consistency between the core structure and the emission modeling at millimeter wavelengths. This is a crucial distinction. It is not enough to say that a fermionic core produces a shadow-like feature. The feature must match the observed thick ring diameter under the same mass-to-distance scaling used in the EHT analysis. If the predicted angular scale deviates substantially, the model is placed under tension unless additional adjustments are introduced. Finally, there is the question of surface behavior. A fermionic core is horizonless. Whether it behaves effectively like a surface, or whether infalling matter can be absorbed without reprocessing in a way that violates spectral constraints, depends on the detailed microphysics of the configuration. The EHT surface tests disfavor luminous thermal surfaces at this scale, so any fermionic core must avoid producing such signatures. That is a thermodynamic constraint layered on top of the gravitational ones. So where does that leave the RAR fermionic core model? It demonstrates that S2 alone does not uniquely identify a black hole. With sufficient compactness, a fermionic core can replicate the S2 orbital behavior within current precision. But the model lives in a narrow corridor defined by compactness, emission consistency, and thermodynamic behavior. It must remain stealth across multiple radial shells and match the exact thick ring observable, not just a proxy for it. In persistence terms, the fermionic core survives some constraints by becoming extremely point mass-like. The question is whether it can remain that compact while simultaneously satisfying the imaging and surface constraints as precision improves. That tension defines its future. Section 4, Mini-Boson Star. The third model we consider is the mini-boson star. Unlike the fermionic core, which relies on degeneracy pressure from fermions, the mini-boson star is built from a scalar field. It is a self-gravitating solution of Einstein's equations coupled to a complex scalar field with a simple mass term and no self-interaction. The structure is horizonless. There is no event horizon, no singularity in the classical sense. Instead, the object is a macroscopic quantum configuration stabilized by the balance between gravity and the field's dispersive properties. From a distance, a sufficiently compact boson star can resemble a point mass. At radii much larger than its core scale, the exterior gravitational field can be close to Schwarzschild. That is why boson stars are often discussed as black hole mimickers. If the object is compact enough, stars orbiting at hundreds of astronomical units may not immediately reveal the difference. So, at the level of S2-like dynamics, a mini-boson star can, in principle, survive. If the configuration is tuned to be highly compact, the change in enclosed mass across the S2 radial shell can be small enough to preserve near Keplerian behavior. In that sense, it shares the same strategy as the fermionic core, become sufficiently point mass-like over the observed orbital region. But the differences begin to matter as we tighten the constraints. First, the internal structure of a boson star introduces additional degrees of freedom. The compactness depends on the scalar field mass and the specific solution branch. Rotation can introduce further structure. Unlike Kerr, where the multipole structure is fixed by mass and spin, a boson star's higher moments are not locked into the same simple relation. As observations push to tighter periapses and multiple stellar orbits, sensitivity to multipole deviations increases. The more we probe the inner gravitational field, the more finely the structure is tested. Second, imaging becomes strongly model-dependent. Boson star images can display central depressions and ring-like emission features, but the morphology depends heavily on the assumed accretion flow and radiative transfer prescription. In some configurations, the scale of the central dark region can approach the Kerr photon ring scale. In others, the image differs more noticeably. The critical issue is the same as with the fermionic core, matching the exact thick ring diameter measured at 230 gigahertz under the known mass-to-distance scaling. The Event Horizon Telescope does not report an abstract photon sphere radius. It reports a reconstructed thick emission ring with a specific angular diameter. For a mini-boson star to close this constraint cleanly, it must reproduce that observable within the EHT posterior while using a physically consistent emission model. Producing a similar-looking image under a different definition of shadow is not sufficient. The observable must align. Then there is the surface question. A mini-boson star does not possess a hard material surface in the way a neutron star does, but it is also not a black hole. The behavior of infalling matter depends on how the scalar field configuration interacts with baryonic plasma. Any effective reprocessing of accretion energy that would produce a luminous surface-like signature must remain below current spectral and size constraints. As with the fermionic core, this is not automatically fatal, but it imposes thermodynamic boundaries on viable configurations. So where does that leave the mini-boson star? Like the fermionic core, it can survive at large radii by mimicking a point mass. It can, under certain assumptions, generate ring-like images, but it carries additional structural freedom, and with that freedom comes additional exposure. As constraints tighten, particularly in imaging and in tighter stellar orbits, the parameter space that remains viable can narrow quickly. In persistence language, the mini-boson star can endure under some conditions, but it must do so while satisfying a growing set of independent observables that probe both the gravitational geometry and the thermodynamic behavior of the central region. The question is not whether it is mathematically allowed. The question is whether it remains closed under all constraints simultaneously. Section 5, Constraint Dashboard and What Moves the Needle. Now we step back. We've laid out the observables. We've described Kerr, the fermionic core, and the mini-boson star. The question now is not which one is more interesting. The question is which one closes under the full constraint set, and what would actually change that ranking. Start with S2. All three models can, in some regime, reproduce the overall orbital shape of S2. Kerr does so naturally. The fermionic core and the mini-boson star can do so by becoming sufficiently compact that the mass gradient across the S2 radial shell is negligible. At the level of present precision, S2 alone does not uniquely distinguish between a true event horizon and an ultra-compact horizonless object. But S2 also places limits on extended mass inside its orbit. That limit is radial shell specific. It constrains how much mass can be distributed between roughly 100 and a few hundred astronomical units. Kerr trivially satisfies this by concentrating essentially all mass at the center. The fermionic core and mini-boson star must ensure that their internal structure does not introduce a detectable effective mass difference across that region. They survive here only if they remain extremely compact, relative to the scale being probed. Now move to imaging. The Event Horizon Telescope gives us a thick emission ring at 230 gigahertz, with a measured angular diameter under a known mass-to-distance scaling. Kerr predicts a gravitational scale that lands naturally in that range once the independently measured mass is inserted. The image morphology is not an afterthought. It is consistent with general relativistic magnetohydrodynamic simulations using that geometry. For the fermionic core and mini-boson star, the situation is more delicate. They can produce central depressions and ring-like structures, but matching the exact thick ring observable requires more than qualitative similarity. It requires that the angular scale, under the same mass and distance, falls within the EHT posterior without ad hoc tuning. Until those models are run through the same feature extraction and calibration logic as the Kerr case, they remain in a proxy category rather than a closed category. Then there is the surface constraint. Kerr has no surface. That automatically avoids the problem of reprocessed accretion energy emerging from a hard boundary. Horizonless models must ensure that whatever effective boundary behavior exists does not violate the spectral and size limits already in place. This is not an abstract philosophical issue, it is a thermodynamic one. So where does that leave the ranking today? Kerr closes the current constraints with the fewest moving parts. The fermionic core survives in a compact corridor that preserves near-point mass behavior at the S2 scale, but faces pressure from imaging consistency and radial shell probing at other scales. The mini-Boson star can mimic some aspects of both, but carries additional structural degrees of freedom that must remain tightly controlled as observational precision increases. Now, the more important question, what would actually move the needle? There are two clear levers. The first is imaging closure at the level of the actual observable. If a non-Kerr model were run through the same 230 gigahertz thick ring pipeline under the same mass-to-distance scaling and shown to land cleanly within the EHT posterior without artificial parameter adjustment, that would materially strengthen its position. Conversely, if improved imaging, especially with higher resolution or longer baselines, revealed structures uniquely predicted by Kerr and absent in alternatives, that would tighten the case for the black hole interpretation. The second lever is dynamical probing at smaller radii. A newly discovered star with periaps significantly inside S2's orbit would probe the gravitational potential in a region not yet fully tested. If its orbit showed deviations inconsistent with Kerr's fixed multipole structure, that would be profound. If instead it continued to follow the predictions of general relativity with no additional mass gradient, the allowed parameter space for compact horizonless models would shrink. Notice something important here. We are not waiting for vague surprises. We are waiting for specific measurements, a tighter orbit, a cleaner imaging calibration, a direct closure of the thick ring observable for alternatives. That is not a position of uncertainty. That is a position of clarity. We know exactly which data would change the model ranking, and we know which data would not. In persistence terms, the models that survive will be the ones that close under all these independent constraints simultaneously without proliferating degrees of freedom as each new measurement arrives. Everything else is narrowing space. Section 6. We began this episode with a simple idea: persistence under constraint. At the center of the Milky Way, we are not dealing with philosophy. We are dealing with orbital mechanics, interferometric imaging, and thermodynamic limits. We have a central mass measured from stellar motion. We have a relativistic precession that matches general relativity within current precision. We have a thick emission ring at 230 gigahertz with a specific angular diameter under a known mass-to-distance scaling. And we have constraints on how a compact object may or may not reprocess accretion energy. Those are the pillars. Kerr survives them cleanly. It requires the fewest assumptions. It does not need additional internal structure to explain S2. It does not require a special compactness corridor to suppress a detectable mass gradient. Its gravitational scale aligns naturally with the observed ring diameter, and it does not introduce a luminous surface that must be hidden. The fermionic core demonstrates something important. S2 alone does not force us into an event horizon. With sufficient compactness, a horizonless configuration can mimic a point mass across that radial shell, but it survives only if it remains stealth at each scale that is tested. It must align with the thick ring observable. It must respect surface constraints, and it must remain consistent as tighter stellar orbits probe deeper. The mini-Boson star carries similar strengths and similar vulnerabilities. It can resemble a compact object from afar. It can generate ring-like images under certain emission prescriptions. But as the data become more precise, every additional degree of freedom becomes a point of exposure. The geometry must align. The emission must align. The multipole structure must align. All simultaneously. So where does this leave us? Not in confusion, not in stalemate, and not in blind waiting. It leaves us in a strong position. We know exactly what would change the landscape. A star with a periaps inside S2's orbit that reveals non-Kerr structure would shift the balance immediately. a fully pipeline-consistent thick-ring prediction for a non-Kerr model that lands squarely inside the Event Horizon Telescope posterior would materially strengthen its standing. Conversely, improved imaging that sharpens the geometry or reveals photon ring substructure would tighten the case for Kerr. Science advances when constraint tightens, and this is the deeper point. Persistence is not about what can exist for a moment. It is about what survives as the net tightens. At the center of the galaxy, models are not competing for elegance. They are competing for closure. Each new measurement narrows the space. Each independent observable reduces the degrees of freedom. What persists is what closes. If you've taken the time to stay with me through this full exploration, I want to thank you. These are not simple topics. They require patience. They require clarity. And they require a willingness to let the data lead. My name is Charles Carroll. This is part of the PIW-CWG Persistence Information Weave and the Carroll-Wells Gradient. Join me next time. Who knows where the science might lead us?